Hey guys, welcome to our next topic. Our next topic is Earth's interior. So we're going to be working on that for a couple days. This is the stuff that a lot of you guys thought we were going to be doing a lot of, or the whole year of. This is going to be the stuff that's inside the Earth. So a lot of this stuff you guys have heard about. We've talked about it a little bit from time to time as we've gone throughout the year, and you've done it in the past before. But we're going to add some more of the technical details using the reference table and stuff like that to help you guys understand. Quick side note, your final exam is scheduled for June 8th and June 9th, 2-day exam, 1 day multiple choice, 1 day short answer, okay? Those are the last 2 days before the end of the year, or 2 of the last days, okay, before the end of the year. So please make sure you mark it down on your calendars now, okay? Make sure you're working on your projects. If anybody has not gotten their time period, please make sure you contact me or Mrs. G for your time periods. But without further ado, let's go. All right, so now we're going to pay a little attention to the inside of the Earth. We've talked a lot about the processes and the events and the stuff that goes on beyond our Earth and on the surface of the Earth, but we've kind of ignored what's happening below the surface. Now, everybody's seen a picture like the one before you, okay? The picture of the Earth cut in half to reveal the inside layers, okay? We saw this when we did the lab earlier in the year when we talked about figuring out the sizes of the different layers and things like that. So when we talk about the Earth's interior, we have to realize it's not uniform. It is different. There are different chemical makeups, temperatures, and pressures as you work your way down. All right, so if we're talking about Earth's interior with regards to the reference table, we're talking about this chart. This chart is located on page 10 of your reference table. Now, this is the actual one that's in your reference table, but I actually want to give you one that's color-coded that makes it a little easier to see, and that is this one. All right, so if we're looking at this, you might want to color code yours as well because it makes sense. This gives you a section, like a slice of the Earth under North America, Atlantic Ocean, okay? Just to give you an idea of what's going on. So if you look here, you have this thin black line right here. That thin black line would be the crust. You see how much smaller it is, okay? And then you've got the mantle, which is here, right, underneath it, right? And the rigid mantle and the crust make up what we call the lithosphere. So you see these two things would make up what we call the lithosphere. Underneath that, you've got the asthenosphere, which is the plastic mantle, okay? And this is the mantle that can flow and bend and move a little bit. And then below that, you have your stiffer mantle. Below that, you have your outer core and your inner core. You should remember this from the lab we did way back at the beginning of the year. In terms of actual depth of the different layers, you have them right here. So if you look right here, all the way down at the bottom, you have the different depths in kilometers. So if you're asked a question, you can use this chart to figure out the depth of it, or the differences, or how far it takes to go from one layer to another layer, just by looking at the x-axis in this chart. Okay? A couple other pieces of information if you're looking at here. Okay, and we will talk about this. You've got different crusts here. So you've got, for example, North America, which would be the continent. Okay, and then over here, you've got the Cascade Mountains. Regents loves to ask questions about that. You've got a trench right off the Pacific coast. You've got the Mid-Atlantic Ridge here in the middle of the Atlantic Ocean. If we're looking over here, this is an important chart, and we'll talk about this in much detail as we're going through this. The density of the different layers. As you go deeper and deeper down inside the Earth towards the Earth's center, the density increases. Sorry about that. Okay, the density increases. So if we're looking up here you have the density of continental crust versus the density of oceanic crust. Okay, you see oceanic is denser. We'll talk about that in a second. Okay, and then you have the boundary between the crust and the mantle, what's called the Moho line, Mohoveric, but we just call it the Moho line. Okay, and then you have the density of the mantle. This would be the upper mantle going down towards the stiffer, or through the stiffer mantle. This would be the density of your outer core. This would be the density of your inner core. Okay, your upper crust and stuff like that is mostly made up of silicates. When you get into here, you're talking mostly olivine and things like that. Okay, when you go to the outer core, you're talking iron, and when you're talking inner core, you're talking iron and nickel. Okay, other things that this chart can tell you. If we look over here at the y-axis, there are actually two y-axes here with two lines. Okay, important that you understand them. The first one is pressure, and the pressure is in millions of atmospheres. So if you're right here at this point at the crust, your pressure is not a million atmospheres. It's like 1 atmosphere. Why? Because you've got the air squishing on top. As you go deeper and deeper and deeper and deeper and deeper, you see that the pressure increases. So this is a direct relationship. The deeper you go inside the earth, the more your pressure rises. Okay? If you're asked at any particular depth what the pressure is, you would use the x-axis and see where it hits the line, and then go right across. So you would go like this and then like this to figure out where it does. Okay? This down here represents temperature. Now, as you go deeper and deeper and deeper down inside the earth, the temperature increases, but it doesn't increase at the same rate. It's not a steady rate. It fluctuates. Okay? When you go from the outside of the crust through the asthenosphere, you see it rises incredibly fast. And then as you work your way down, it continues to rise, but not at the same rate. Okay? The reason why is the pressure has an effect on how the temperature changes. Okay? It should go like that, but it doesn't. Okay? The actual temperature goes like this. And so that's going to affect the melting points of different rocks, whereas a rock would melt on the surface of the earth under the pressures that you find down here, it's going to stay solid. It'll be like semi-plastic, which we talked about before, which is what lets a lot of the interesting stuff that happens inside our earth actually happen inside the earth. And if you look, okay, your highest temperature is right here inside the earth's core, and you're at around 6,500 degrees, give or take. 6,800, I think, actually, right? At about 6,500 kilometers down. All right, so we're going to talk about the Earth. We got to talk about the outermost layer of it first, which would be the crust. Now, this is the layer we've talked about a lot. This is where all the action, all the weathering, the erosion, glaciers, all the stuff we've been talking about happens. So we've talked about it a lot, or at least what affects it, but we haven't actually talked about the crust very much. So when we look at the crust is the thinnest layer of the Earth, okay? Usually only goes up to about a depth of 70 kilometers at best, okay? And it's where all the volcanism and earthquakes and all that stuff are visible. It's not necessarily where they're formed, but it's where they're all visible. Okay? Now, if we're talking about the crust, we have to understand that the crust isn't uniform. It's actually, there's different types of crust. There are actually two main types of crust, that being continental crust and oceanic crust. And in order to differentiate between the two types of crust, there are three main properties that we look at. Those three properties are rock composition, so what is the crust made out of? That identifies it as one or the other. The average thickness of that type of crust, and the density of that crust. Those three properties are what allows us to understand the differences between them. Now, the first property is the rock makeup. Continental crust is typically granitic. It's made out of granite, which is the rock that you see on the left side of the picture from Yosemite National Park. Okay, continental crust tends to be granitic in nature, whereas oceanic crust tends to be basaltic, made of either basalt or gabbro, depending on the type of event that formed it, which is what you see on the right-hand side of the picture. Okay, and so continental crust tends to be lighter in color, and oceanic crust tends to be much, much darker in color. Now, the next property is the thickness. The thickness of the crust is also a determining factor of what we're looking at. Continental crust, like you see in the picture before you, can be incredibly thick, particularly if you're talking about underneath mountain ranges like the Himalayas or the Rockies or the Urals. It can be up to 70 kilometers thick. On average, it's about 12 to 15 kilometers thick, but underneath mountains, it can be up to 70 kilometers thick. Oceanic crust, on the other hand, tends to be much, much thinner. Like I was saying, it's usually about 7 kilometers thick, but it can be as thin as about 2, some places even 1 kilometer thick. And so the thickness of the crust that you're looking at is going to be a determining factor, okay? Like you see in the picture before you as well. And once again, if we go back to that picture we were looking at before, density is another huge property. Oceanic crust tends to be much, much denser. It tends to have a density almost of 3 grams per cubic centimeter. You can actually see this on the reference table on page 10, whereas continental crust has a density around 2.7, 2.71, 2.72, which is the typical density of granite. This actually causes the continental crust to be much less dense than the oceanic crust, and that's going to be important for when we start talking about plate tectonics and things like that. Now, when we look at the crust, we have to realize that there's a couple of rules or a couple of ideas that are of critical importance. The first of these is what we call the principle of original horizontality. big fancy sounding word, but what it basically means is that most rock layers get laid down horizontally, like pieces in a sandwich. Okay, you typically don't put the cheese and the meat and the lettuce and tomato in a sandwich vertically. You don't stack them like that. You don't jumble them all together. You lay one layer on top of the other on top of the other. That's what the principle of original horizontality says. It says when sediments or lava flows or things like that are laid down, they typically are laid down in a horizontal stacking pattern. Okay, so when you look at the picture in front of you, you see that you've got these different layers of rocks that are laid like this. But one thing scientists realize is that while they may have been laid down originally horizontal, as time goes on, the earth and the movements of the earth and the energies from the inside of the earth can warp and twist these. And so what you can get is something that we call folding. And what happens with folding is that the forces inside the earth cause the rocks to bend. Now they cause them to bend, not to break. And so what you end up with is these huge folded, curved, bent sections of what used to be nice horizontal layers of rock and is now bent and twisted. And that gives you an idea of the pressure and the energy and the heat, everything that had to go into doing these things. And so folding is when the rocks actually bend under the pressure that's applied to them, like you see in the picture before you. Just for reference sake, if you look down at the bottom, you'll actually see a small little card, give you an idea of the scale of what it is that we're looking at. Okay, obviously this layer was buried deep below the earth where the temperatures and the pressures would allow something like this to happen. The second thing that can happen is, well, sometimes you can apply pressure to a rock and it breaks, it cracks. Okay, this is what we call faulting. Faulting is when you have breaks in the crust. It's a weak spot in the crust where the pressure got too much and the crust broke. Okay, and that's what you see in this picture here, this large crack that runs through the layers, and you see how the layers are all offset. You can tell that they originally used to be stacked next to each other, but they are now offset from each other. Okay, and in the picture you see now, you'll actually see a fold and a fault. So you can see the rippled fold, and then you can see how all of a sudden it looks like it drops off. Well, that's because there is a fault. So if you track the red line, you can actually track the red line into the fold on the other side of the fault, but you see how it has dropped away from it. So when we talk about, folding and faulting and things like that, what we have to realize is the forces that we're talking about. Okay, one is when the crust is bent upwards or downwards, and the other one is when the crust is actually broken. So the next layer is the Earth's mantle. And the Earth's mantle, we don't know that much about it because we've never actually been to it, but we've learned lots about it by studying volcanoes and things like that. The Earth's mantle is primarily made out of olivine and periodotite, which are two rocks that we have seen before. There are two layers of the mantle. There's the upper mantle, which is the plastic mantle, which can move a little bit. And then there is the lower mantle, which is a bit stiffer. Okay, they're both made up of roughly the same thing, but the pressure and the heat are different. Remember, as you go down, it gets higher pressure, higher density, higher temperature. You can actually find that density on the reference table on page 10. Now, when we're looking at the inside of the Earth's mantle, what we will see is that the interior of the Earth's mantle moves. Now, why does it move? It moves because of convection cells. We talked about convection cells before. Convection cells are these alternating bands of hot and cold material rising and sinking, creating these big loops like you see in the pictures before you. That is how material moves inside the Earth. The mantle that is closest to the core, down towards the bottom, or towards the center I should say, is going to be much hotter material. That hot material is going to rise up through the mantle. The mantle that's touching the crust is going to be cooler. And so that material is going to sink down. And so what you create are these giant loops, these giant convection cells. And those giant convection cells are incredibly important for things like plate tectonics. They're the driving force behind it. They sometimes can punch holes through and create things like mid-ocean ridges or rifts. Okay, and so they are incredibly important for the movement of material through our crust. The final layer that we're going to talk about is the core. Now, the core of the Earth is made up of nickel and iron, but there are two cores. There is the liquid outer core and the solid inner core. You can actually see both of them in the picture in front of you. And the fact that we have this layering of liquid surrounding a solid core actually helps us to generate our magnetic field, which we've talked about on numerous occasions with auroras and compasses and things like that. So our core creates what we call the dynamo effect, which is why we have a magnetic field. All right, guys, so that does it for today's lesson. Please make sure you paid attention, and I'll see you guys tomorrow. All right, guys.